So I'll just, because I don't really recall exactly where I stopped. I think we discussed a unitary operator and making and the diagonalization. So we proved that if we have a Hermitian or a unitary operator, then so for a Hermitian 8 or unitary, I'm going to write this unitary as A, there will be bases where they are diagonal, and there will be corresponding unitary operators U, which are essentially the change of basis operators, which give us, so if you have this U, this let's say H, there will be some unitary, so that when you do U dagger U, you get a diagonal matrix. And similarly, for this unitary, you will have some other unitaries, so it gives you the diagonal. So you can always put, you can always go to basis where the matrices representing these operators, they become diagonal. So let me just do, although all of this, I'm kind of assuming that you have good practice in linear algebra, but let me just do a few examples very quickly. So you consider an operator defined via this matrix. So that means if I say that it's defined by this matrix, it means that these are the matrix elements of this operator in some basis. There's some basis, and I just name it. I call the basis elements. It's a 3x3 matrix. That means it's living in a 3-dimensional space. I call the basis elements where its matrix elements are these as 1, 2, 3. Then I want to know what are the eigenvalues. So all you have to do is do this. And compute this determinant and put it equal to 0. So when you do that, you get 1 minus lambda, 2 minus lambda, 1 minus lambda, and then minus times 0, then plus times 1, and then 0 minus 2 minus lambda. So this is the polynomial which you get through the determinant. So I can take this 2 minus lambda out. I get 1 minus lambda square and minus 1. So this I can write as 1 minus lambda plus 1 and 1 minus lambda minus 1, because this is 1 minus lambda square minus 1 square. So you get a plus b into a minus b, and this is 0. So square, this is same as that, and from here you get minus lambda. So this gives you 3 roots, but 2 of them are repeated. Because it's a squared term, that means you have 2 roots from here. 2 and 2. And we can look at the Eigen Vectors. So the first one corresponding to the 0 eigenvalue, these are its components in this basis. I'm just assuming them. And I'm multiplying it with a 0, because that's the eigenvalue. So this gives me V1 plus V3 is 0, 2V2 is 0, and V1 plus V3 is 0. So this gives me V2 is 0, and this just gives me V3 is equal to minus V1. That means all that you require, you give some arbitrary value to V1, then you have like this. So the eigenvectors are of this form with the eigenvalue 0. So as is always the case that the eigenvectors, they always form at least one-dimensional space. You can take the eigenvector, multiply it with any number, you still get the eigenvector. And since the value 0 occurs only once, so you get a one-dimensional space. The other one is repeated, so you will get a two-dimensional space. Now, if I look at the other eigenvalue, which is 2, this gives me V1 plus V3 is equal to 2V1, 2V2 is 2V2, and V1 plus V3 is equal to 2V3. So this doesn't give me any condition on V2. V2 is free. And this tells me that V3 is equal to V1, and this tells me V3 is equal to V1. So all you have V1, if you fix V1, V3 is fixed. So V3 is fixed, but V2 is free. So your eigenvectors, you can write them like this. And since this guy and this guy are linearly independent, so they are forming a two-dimensional subspace. So as we had proved, if you have a repeated eigenvalue, you will get that many dimensional subspace as the eigenspace. You choose any alpha and beta, you will get an eigenvector. Every vector in this subspace is an eigenvector with eigenvalue 2. These two guys, they are orthogonal. So they give you an orthogonal basis in this subspace. But if you choose any other values, give two values to alpha and beta and pick two linearly independent vectors over here, then those in general will not be orthogonal. So you can pick a non-orthogonal basis as well. Now, you may ask the following question. That I found this eigenvalues in a particular basis, writing the matrix in a particular basis. How do I know that if I had written the matrix of this operator in some other basis, will the eigenvalues change? Well, to do that, you can note this. So these are like, again, some small practice problems that under a unitary transformation, determinant of a matrix does not change. So if you have determinant, if you have an operator, let's say omega, and you compute its determinant, and then you compute the determinant of this guy. You multiply this matrix on two sides by a unitary and its Hermitian conjugate. Then by determinant properties, they break up. On the other hand, if I use the unitarity property, which says U dagger U is identity. So if I do U dagger, if I take the determinant of this guy, this is 1, determinant breaks. So that means the determinant of U and U dagger are inverses of each other. So this guy is 1. So determinant does not change if you make a unitary transformation, and unitary transformation correspond to change of basis. So, for example, you can say that if I take this operator omega, not operator, now you make a matrix out of your operator in a basis, and you compute this thing. This will give you a polynomial. And this polynomial you put to 0, it has unique roots. Unique n roots depending on the dimensions. By unique, I mean that set is unique, not that each one of is different, but that whatever set of n roots you get, that's unique. You cannot replace it with any other set. Now, if I consider this guy, transformed operator, transformed matrix. So this is the matrix of this operator in some other basis, because now I have transformed it to the unitary, which takes it from its current basis expression to some other basis expression. But over here, we are thinking of it as a new matrix, which we have got by doing this kind of operation on the original matrix. And find the eigenvalues of this guy. But this I can write U dagger iota U, because U dagger U's are unitary. So I can always bring them, U dagger times U is identity. So I can put it there. And then I can write it like this. But this we just proved is equal to that when you put U dagger U inside the determinant does not change. So that means this guy has same polynomial, gives you same polynomial as original, this guy. So that means if you write this, the matrix of this operator in any basis, you will get the same eigenvalues. Now you can also prove this nice result that for a Hermitian or unitary operator, the determinant, which we know is basis independent. So determinant of H, if H is Hermitian or unitary, I'm denoting both of them as H, is equal to the product of eigenvalues. So how do I show it? Because I know that for a Hermitian or unitary operator, a U exists. There exists at least one basis. We know that there are many bases, but they exist. We proved it that exists at least one unitary operator, one basis where the where if I construct this U by just collecting those basis vectors like this, then U dagger HU will give me a diagonal matrix. This we know. So then I can take the determinant and I also know that on the diagonal, on this diagonal elements have eigenvalues of original H. That's how the diagonal is constructed when you go to this basis. So this determinant of HD is just the product of eigenvalues. But I know that the determinant does not change under unitary transformation. So this is equal to determinant of H. So that means determinant of H is just the product of eigenvalues. Similarly, you can very quickly show that the trace of H, if H is Hermitian or unitary, is the sum of eigenvalues. Again, trace of U H U dagger is equal to trace of, because such U exists, so that this product becomes the diagonal with eigenvalues on the diagonal. This is just the sum of eigenvalues. But over here, because of the cyclicity of this trace, I can bring the U dagger over here and this becomes 1. So that means this is equal to trace of H, which doesn't look diagonal in this basis, but we know that once I will compute the trace, even in this basis, its sum of eigenvalues, it will just be equal to the sum of eigenvalues. Now, I want to consider some more operators. Well, did I write the second postulate? The second postulate was that to for each observable, there is associated a Hermitian operator. So let's write postulate 3. We will get the full understanding of it when we do some examples, but right now I'm just going to write it and explain it briefly. When you make an observation, an observable on a system of an observable whose associated Hermitian operator is, let's say, omega hat in a state when you make an observation of an observable whose associated Hermitian operator is omega hat on a system which is in state psi, then you will get one of the eigenvalues of the operator omega hat as an observation. Now, what is this saying? What's an observable? We had discussed it before. It's some physical question you ask, any question, which reasonable question which you can ask about a system, and it's knowable, measurable in some sense. That's an observable. So, for example, speed of a particle, position of a particle, angular momentum of a particle, color of a ball, age of some person, anything which you can measure and give a sensible answer in principle. You can ask for a sensible answer for anything. That is an observable. So that's an observable. Anything measurable. What's an observation? Observation is that you are not just theoretically predicting. You go, you have an apparatus, and you actually go and measure it. And it doesn't matter what kind of apparatus you have, you're doing the best job you can do. But observation would be like if you are measuring the speed, so it would be something like a speedometer. There will be a needle which will tell you what is the speed. It will give you a number. If you are asking for the color of an object, there will be some reading, some apparatus which can detect the color, and it will read for you what the color is. So something you do on the system and some experiment you do on the system, and it tells you some answer. The apparatus tells you what is the observation, what is the answer for that observation. So that's an observation. And you're doing it on a system. So system of interest, it could be a ball, a particle, an electron, anything you like. And as per our first postulate, the system has to be described by a vector in the Hilbert space. So the vector is in Hilbert space psi. The postulate says no matter in what state the vector, the system is, when you will make an observation, you will get one of the eigenvalues of omega. So omega has a list of eigenvalues. Could be infinite or finite. And this is called the spectrum of omega. So you will get one of these eigenvalues as a result. So, and why our postulate, why this shows that why we chose the postulate 2. Why did we take Hermitian operators? Because if the operator is Hermitian, this list of eigenvalues is real. And you are asking for some physical quantity, and physical quantities, they are all real. So like you are asking for what is the momentum, what is the position, what is colors, you can give them a listed name, listed numbers, red is 1, green is 2, and so on. So whatever question you will ask as a observation, your meter reading will give you some real number. So you want, so this postulate then tells you that you will pick one of these real numbers, which are associated with the Hermitian operator of that observable. So each observable will have its own Hermitian operator acting on the Hilbert space. And what you can get as an answer would be one of the eigenvalues. Now, we have proved, no, I think, did we prove it that uh, eigen vectors of a Hermitian operator form a basis? Did we prove it last time? I don't really recall, so I will not go to the, let's say that this is postulate 3a. I'll go to postulate 3b, but before that, I want to consider some more operators which I want to construct some more Hermitian operators. But before we go there, I will not check the Hermicity right away. I just want to discuss what kind of operators they are. So we had the Hilbert space. So we have Hilbert space. So we are considering different kinds of Hilbert space. We had this, what you can say, C2. What is C2? This is just a space of this form. Two complex numbers put in a column. Two-dimensional vector space with complex coefficients. Similarly, Cn would be n-dimensional vector space with complex coefficients. But we also had Hilbert space with infinite dimension L2AB. Square integrable functions on AB. Well, what would be the most important space for us would be actually this one. Square integrable functions on real line. And we had, so the elements of this are functions, but as per our convention, we are considering them as some abstract vectors. So we are writing them as some cats. So these are things like these, some cats. And we had expanded them in this basis. Them in a basis X. This was called the position basis, where this was defined through this property. That this is how it's normalized, that it's a continuous basis, and the scalar part of X, these X are real labels. Take value in the real line all values in real lines are possible. And when you take two different numbers, you get a 0, and as they approach to each other, you get a delta function. You get a peak. So this scalar product is given by a delta function. And with this normalization, we had expanded that we can expand any function. This is just the definition of the spaces, like this. And these guys, values of f at point x is considered as the component of this abstract vector in this x direction. So in a sense, you are collecting the values of f at each point. And these values should be thought of as components of f along the direction x. For each point on the real line, you have a basis vector, and the values of f at that point is just the component of the f along that basis vector. Is there a question about it? So now we also saw this, that with this interpretation, I can compute this. So taking this expansion, if I take its scalar product is linear, so these numbers come out. So this is just that same statement that the component, this is the definition of component. Component of f along x dash is just this f of x dash, the value of f at that point. And this also shows that this is taken to be, by definition, the way I have normalized it, it's an orthonormal basis with this particular normalization. And then we had, so now I can define, I think we hadn't discussed this. So like I had this, that if I have an orthonormal basis, I can so write take the orthonormal basis vectors, then this is an identity. So I can do the same thing with this orthonormal basis. And sum over all these eigenvalues, which in this case will be done to an integral. We can verify that it is indeed identity, because if I apply it on any vector in the Hilbert space, I get this gives me f of x as per this, and then this has x, but this is just this expansion. So this gives me back f. So this is indeed identity. Now consider another basis in this space. I'm just defining another basis by its various properties and define it in a consistent way called K basis, such that, so these are some vectors, set of vectors, which I'm claiming that it forms a basis, that you can expand any vector in terms of this. And I'll just show by hand that it is indeed forming a basis. But first I want to define the basis. So the vectors will be denoted like this, K, and these Ks are again a continuous parameter taking values in real line. So you again label it by some number, and that number, to exhaust the basis, you have to consider all possible real numbers. But this is not those vectors which were the x vectors. These are some other vectors. And the way I define them, I can define a vector by giving its expansion in terms of x, or in other words, by giving its components. So I say that its components are these guys. If these are the components, then I can expand it like this. So out of my old basis, I have made some linear combinations. This is my old basis, the position basis. I can multiply it with some uh, coefficients from the complex plane, complex numbers, and add them up to this integration. And that should give me a new vector in the Hilbert space. Well, first of all, well, a new vector. Later we will see that these guys actually do not even exist in the way we have defined the Hilbert space, but we just throw in by hand because these are very useful. In any case, if I think of it as a linear combination, so I have made some linear combination of my old basis to get some new vectors. Now the claim is that I can expand any vector in this space in terms of the K basis. K vectors form an orthogonal basis. In this Hilbert space. Well, first of all, let's see what is their normalization. So if I pick two of them and compute the scalar product, so I get 1 over under root 2 pi. Everything over here is real, but when I do this bra operation, so let me go step by step so that you don't get confused. One of them, I expand E iota the other is sorry, this was K dash and this is K. Now when I do this, this guy becomes E minus, because you remember when we take the conjugate, then the coefficients which come in front of the vector, they are complex conjugated. In the next step, I'm going to sandwich this guy with this guy. But then I have a sum over the index x and a sum over this other index x. So I better, do the counting properly, I should change this dummy variable. So I'm going to call it x dash. This is the integration variable. I can call it anything, but I have to make sure if I'm multiplying, I use two different ones. So you get dx and dx dash. And you get E minus iota k dash x dash E iota k x, and then x dash x. This thing is just delta function. Sorry, this is so this is a delta function. Let me do one of the integration. Let's say I do integration over x dash. When I do integration over x dash, dx integration is still there, and this x dash changes to x. So I get this thing, and everything else is gone. Now, what is this guy? So if you recall some identities from the delta function, this is a delta function actually. If you have this, normalization is important. You have two variables. You do integration over one. Doesn't matter if there's a plus or minus, because delta function is even. Let me write it like this because it's written like that. Then this is a delta function in B. It's a very useful and famous identity. So that means these guys, they have exactly the same kind of normalization as the position basis. Also, any f, consider any f in space, I'm gonna see if I can write it as a linear combination of these vectors, k vectors or not. So suppose it's possible, and I can write it like this. So I will have some, since it's a continuous label, for each continuous value of k, I'm multiplying with some complex number, which is labeled by a continuous variable k. I can write it probably like this, but I'm not writing it like this because I don't want to get the confusion that it's the same, because remember, I'm writing these guys as f of x. And these are the functional values of, these are the values of function at point x. But these guys, they will not be the values of function at point k. So to avoid this confusion, I could have probably put a tilde over here, that is some other function. For each value of k, I get some number. So I can write like that, but for now I'm writing like this. Or maybe I can write like this, that would be fine too, probably better. Now I just need to know, so if I do this, this I just found is this. So that means these numbers are well defined, and just the scalar products of this vector f with the corresponding vector k dash. So you can expand any of them like this, because all you have to do to pick these numbers which you have written in your expansion is to take the scalar product of f with the corresponding k dash. But I can also see what they are, and that will show us that they actually do exist. So what are these fk's? What are, okay. So I take this and assume that I can expand like this. Now hit it with an x from the left with this basis. This goes out. Now xk, this we know what it is. Okay, these are f of x, values of function at point x. And xk gives me an under 2 pi. And this is eikx. So if you look at it carefully, this is nothing except inverse Fourier transform of f tilde k. And I can start from this expression. This is just starting point. I'm expanding my vector in the position basis. And this guy is defined as f tilde of k. And what is this? So I have hit with a bra of k. This is just, what is this? This is star, if I invert them. So that is E minus iota kx. This is Fourier transform. So what it tells me is that these f tilde k, which come in the expansion of this vector f over here, they are just the Fourier transform of the function. So when I expand in the basis k, I'm expanding in terms of the Fourier transform coefficients. And when I expand in terms of x, I'm expanding in the original function as coefficients. And the two things are the Fourier transforms of each other. I can go from one to the other through a Fourier or inverse Fourier transform. And you can see some of these techniques. For example, you can do the change of basis by using this kind of thing. So first of all, I had this identity as this, but now I will also have this as identity because this is also an orthonormal basis. And it's almost all of these things are almost by construction. This is just giving a more kind of a abstract look to the Fourier uh, expansion. Because if I apply like this, what's happening? This all comes only from the normalization of these. This is just by definition. This is equal to f. But you can use it to change basis. For example, if I start with this guy, this expansion, so this vector is written in the x basis, or what you call position basis. I apply the identity with this resolution. So identity is acting here. I write it as, because it's linear, so it goes through all these numbers. I resolve it in this k basis. Now this guy, so remember when you have kx, the x component of k, that's eikx. And when you flip it, you are essentially taking a complex conjugate. But you can think of it as the kth component of the vector x. So this gives me dx, and this gives me e minus I k of x. There's a 1 over under root 2 pi. And then you have a k left over. Now, if I combine these, so I started with an x basis. But if I combine this thing, let me write this dk over here and combine these guys. So what is this? This is just the Fourier transform of this is over here. Fourier transform of f of x which is exactly the expansion of f in terms of k basis. Because that's what we have discovered, that with this k basis defined through these equations, the expansion of coefficients of your vectors in this basis are just the Fourier transforms of the original functions. Any question about so far?
No, sir.
Sir, means that when we change the basis, we are applying Fourier transforms.
Well, essentially, yes. So you can, instead of writing these basis vectors all the time, you can say, for example, like in linear algebra, what we can do, we instead of working with abstract vectors, we can just work with components, right? Pick a basis, stick to a basis, and then you can work with components. So similarly over here, you pick a basis. So let's say I say I'm picking x basis, then you can work with f of x. But just like over there, you can change the basis and go to some new basis and work with components over there. That's completely fine. You're still dealing with the same vector, just in a new basis. So over here again, you can change to k basis. And over here, the components are the Fourier transforms. So in practice, you don't need to always write in this abstract notation. In practice, you can say that I'm just going to work with components. So you can work with, in this Hilbert space is in the end a Hilbert space of functions. So you can work with the functions originally, which you think of them as components in X basis, or you can work with their Fourier transforms. And we know that Fourier transforms equally well define the functions.
Okay, so thank you.
Now, let us consider some operators on the space. Probably I shouldn't have written that postulate because I didn't get the chance to explain it much. Because I'm kind of can't recall. Did we prove it that Eigen vectors of a Hermitian operator they form a basis? Did we? Okay, I'll just go.
No, sir.
I'll look in the notes because that we need to properly discuss that postulate. So, but that's why I wrote it as 4. I'll come back to it and explain it in more detail with examples. But right now, I think let's finish a little bit more about these infinite dimensional Hilbert spaces and some operators on it, and then we will discuss them all together when we write the postulates. Now, let us consider some operators on this Hilbert space. On this Hilbert space, which is L2. And the first one, well, there's some easy, let's start with this one. The other one is probably easier. This, you should think of it as just a symbol. But I can define, I'm going to define this action of this operator. It's a linear operator by definition. It is declared to be linear operator. So if it's linear, then you can define its action on any vector in a basis. And if you know that if you have a vector f, it has an expansion. These are the components. When this k hat x on it, it changes it to a new vector f dash, and that has some components that will have its own expansion. So if I could just tell you the components in the same basis, then you know what is the action of this vector, of this operator on the vector. So I'm defining the action in one particular basis. And how do I define it? I define it that under the action of this k hat, these components go to these components. Where f dash, now I'm doing maybe let me write them as tilde I have used not. They go to this, where this dash stands for the derivative. At point x. So it changes the components of the vector by the derivatives of the function at that point and taking them as the components and multiplied with minus I. I could have defined another operator d which only does this to the components. So this k is minus iota d. So now I want to know that what are the components, what are the matrix elements of this guy in x basis and in k basis. So which one should I do first? Let's do the k. So remember, just like when we had finite dimensional vector spaces, we were defining the matrix elements as the operator sandwich between the basis vectors, and the list of that were the matrix elements. So similarly, we think over here, and I'm interested in something like this. This will be called a matrix element of this operator. Now I'm gonna find them out in a using some techniques. You can do it in many ways. I just tried doing it before the class, and this is how I did it. So it acts on a function and gives you this f naught, and I look at the components of this resultant vector. I know that by definition of this operator, these should be equal to df by dx, or you can say f derivative evaluated at this point x. Now what I do is I bring in, because I want to isolate the XX component. So I bring in an identity. So over here, I have introduced an identity. I can always insert it. And this is equal to this. Now, this thing is only the component of the original vector, which is just the value of f at the point x dash. And it has to, this guy has to give me something so that when I do this integral, I get this thing. So this would be simply equal to delta d by dx dash well, the correct notation is, well, that's okay. And minus iota. Because when I'll do this, I'll get this. So this means is equal to delta x dash minus x d by dx dash. This you can also write as iota d by dx dash delta of x dash minus x. But this is good enough for us. So it gives you something like this. So what is this saying? It's saying that when I act on, what's the use of it? And what does this symbol mean? This is just because of the way we are applying these operators, this delta function comes in. But essentially what it's saying is, if I act on a function and I want to compute its x component, so this is minus iota which is just minus iota. So I can interpret it now in this way, that I applied k hat on f to get f naught. And now I'm looking at the x component of f naught, which is just f naught of x. And I can do it by doing a kind of a matrix multiplication. There's a sum over x dash, which is over here because of this dx dash, sum over dx dash. So what it's saying is that I have done this kind of a matrix multiplication to get this. And but the components which I get finally is just this thing. So if you don't want to write this bracket notation, if you're only working in the in this particular basis, in position basis, you can say in position basis. So this is the statement where we started from. K can be just defined by this effect, that f of x goes to, so it's a derivative operator. And I have just included a minus iota for one particular reason, which will become clear soon. Any question about it? Now let's look at the matrix elements of the same operator, but in the k basis. So you have k hat x on f gives you, this is abstract equation. It's always true. I haven't gone to any basis yet. Now I project it. This is also the language you use. You're projecting it onto a particular basis. So I project it to the kth component of the k basis. And now I introduce, on the left hand side, I introduce an identity, because now I want to compute these matrix elements. K hat bit sandwich between k and k dash. And on the right hand side, let me just introduce this identity. So over here, I can write it like k dash, and this is f tilde of k dash, the component of f along the direction k dash. And over here, I have dx e, there's a 1 over, no, there's no 1 over. Now there will be a 1 over when I compute. And this is just the component of f naught along x, which we just found is just this. Now this f is assumed to be square integrable. That means at the plus infinity, for this to be square integrable, f has to go to 0 as x goes to plus or minus infinity. This is exactly the reason why I say that these x and k are not square integrable, because k's components, they don't go to 0. And we will see what problems it causes and how to deal with it very, very soon. But f, for at this point, all the other things, they are supposed to be square integrable. So they go to 0 as x goes to plus minus infinity. So I can integrate by parts. So I have, and when I integrate by parts, I get kx df over dx minus derivative now x on this guy and brings down a minus iota k. And minus minus gives me a plus. There's a minus here, iota iota. In the end, it becomes a k. This is just f tilde of k. So that means, what should I choose for k hat, k dash? It should be just k or k dash, doesn't matter. It's symmetric in these two. So that when I do this, I get so its matrix elements are these. So this also means that when this x on a basis element, this should just pick up this. Because when I have this, only then I will have same as this. Remember that delta function is symmetric. So that means that in the k basis, this guy, which was a derivative operator, in the k basis, it's a very simple. The k basis, it's eigenbasis. Of this k hat operator. Similarly, we can do the opposite of it to, well, okay. So any question about this? So in the position basis, it has this form that it takes the components, that means the functions, and derivates them. But in the k basis turns out to be its eigenbasis, and whatever the value is written inside the k vector, the basis vector, it brings it out. That's what it does. Now I can define another operator. It's this operator, and this time I'm gonna go in this direction. So I have found an operator so that the k basis is eigenbasis. So let me just define by hand another operator so that the x basis is this eigenbasis. And so similarly, like it's over here, if I compute these guys, this matrix elements, so this eigen basis, they will turn out to be like this. And let's see what happens to the components of any general vector under the action of this operator. So if I take a general vector f and act with x hat, and I want to find what are the components, what happens to the components of this? So originally, F has these components. Now this new vector, if I could just write it as an expansion, I will have the components. So let me just introduce the identity. You can put the identity anywhere you like. So I'm switching it, putting it in here between x and f. So it's an eigen operator, pulls out an x. This gives me f of x by definition, and I'm left with this. So the new vector has these components. Or you could have found them by doing this. These things will give you f of x dash of the new guy. New guy, let's call it tilde. Double zeros when x had x on it. And on this side, I have just introduced an identity. This gives me x delta of x minus x dash. This gives me f of x. And this gives me so both things are saying that if you have a vector and you're specifying it by giving its components in the x basis, which are the functional values, then under the action of this operator, it goes to a vector whose components are wherever you are evaluating it, multiply it by that number. You can also see that what does its effect looks like in the k basis. What I should do is, why don't you try it? So let me give you this problem. I'll solve it next time, but you should try to do it yourself. That I have given you this expansion, that is expansion of f in the k basis. When x had x on it, what happens to these components? The new guy will have some expansion. What is the relation between g tilde and f tilde? So the techniques I have used, try to use them and try to find it. And so now we meet tomorrow at 2, right?
Sir, after 5 नहीं decide हुआ था.
After 5 क्यों होगा? I mean,
कल के लिए सिर्फ only for tomorrow, please.
I'll record it and you can just have a look at it.